Welcome back. You tired of me yet? Right? You're tired of the whole thing at this point? Okay, so what we're going to do in this particular video is we're going to take a look at some of the less traditional polyatomic ions that are on here. So some of the different kinds of groups that are out here. So we'll kind of do a couple of different zones in here. So we're going to cover the oxyanions that have hydrogens added into them, some of the weird binary ones, just to kind of review those really quick, and then some of the ones you just kind of have to memorize. And then last but not least, hi Kat. If we'll talk about the other oxyanions that are possibilities that are out there that will show up occasionally in your packet. So I'm going to buzz through this one a little bit faster. So this is more of kind of what you need to be looking at. How are you going to find these, get them to stick in your brain, etc. Again, if you've got the polyatomic ions sheet for Chem 2, it's posted in the module as a reference sheet. I would grab that thing out because that is definitely a useful form. So in the last video, we talked about the typical oxyanions, and these are the typical ones like chlorate, nitrate, those sorts of things. So we talked about kind of the regular set that's out there. So, things like NO3, which is nitrate, SO4, which is sulfate. And then we talked about some of the ITE forms that were out there. So like sulfite was out there. And we could talk about chlorite, ClO2 with a 1- charge. So we talked about that last time, that ATE means it's got its usual or most common number of oxygens, and that the ITE form had one less than that. We also talked about the fact that there are some prefixes that you could put on there, like per and hypo, that might even modify that number of oxygens further. So there are some other variations that are also possible of some of our oxyanions. I'm not going to ask you to worry about predicting these, but I will ask you to recognize some of these. And these are ones that are oxyanions that have a hydrogen stuck in one of their spots. And these are oftentimes called acidic salts. I'm going to put this one up here. That when these polyatomic ions form ionic compounds, a lot of times they're called acidic salts because they've got this hydrogen in here, and hydrogen is a hallmark of something that acts acidic. So let me give you an example of one of these ones that you may know around your house, which is baking soda. Baking soda, there we go. Baking soda has two common names. Its most common name is this one, sodium bicarbonate. Carbonate. Sodium bicarbonate is its kind of common name, or sodium hydrogen carbonate is the other name for this. So what does this mean when you put the bi in there? So this is a compound that is this, CO3. This is sodium hydrogen carbonate, right? Well, it turns out that this is actually the ion. This forms a different type of polyatomic ion, and it obviously looks very similar to what carbonate is. So carbonate is this, carbonate is this, CO3 with a 2- charge. That's carbonate. If we have HCO3, now we've kind of changed this a little bit. We've plugged a hydrogen in to one of these spots. Now it's 2-, right? But 2- here means that it had to gain 2 different electrons. Well, if hydrogen is bonding in one of those spots, the typical charge of a hydrogen ion is a 1+. So if you think about taking something that's a 2- and bonding in a 1+ to it, the overall charge of this thing now is 1-. In this particular case, when we've got these acidic salts, the hydrogen in there does change the charge. So the naming on this, we can actually use 2 different names to it as well. So again, we've got carbonate, and this one has 2 possible names. I don't care which one you use. The old school name is bicarbonate. NATE, with this prefix on there. Now this prefix doesn't get used all the time. It's kind of fallen out of favor. So there's a more systematic name for it. And that's this one, hydrogen carbonate. ATE, and that's 2 words. So hydrogen carbonate. I kind of like that one better because it is literally hydrogen and carbonate. I love when they make sense. But you'll see this old-fashioned name, this bicarbonate, around. So even on the polyatomic ion sheet, I have it written this way: hydrogen, and then I have like this, bicarbonate. So what this means is you can either call it hydrogen carbonate or bicarbonate. It's never called hydrogen bicarbonate. That's too much, right? So it's kind of one or the other. But I leave this in here because a lot of times your textbook still uses bicarbonate. But again, it's kind of falling out of favor. And using the name hydrogen carbonate is also more commonly done. So they're both fine. You kind of need to learn to recognize that both of them mean the same thing. However, you can pick one that you might use more commonly. So if you like the bicarbonate, great, call it that. If you like hydrogen carbonate, great, call it that. But if it's written and given to you in that hydrogen carbonate form, you should learn to recognize what the Bi prefix means. So there's a couple of other ones that do this. So carbonate and bicarbonate is one big pair. Here's the next one that does that. Pen back here. So we got carbonate and bicarbonate. We also have this one, sulfate. It's got to have enough charge here that we can have a 2- charge. If we put a hydrogen on there, SO4, its new charge is going to change, right? So now it's not a 2-, it's a 1-, right? So this would be sulfate, the top one. This one right here would be called hydrogen sulfate, or bisulfate is the other name for that one. And again, either of those names is correct. So carbonate does this, sulfate does this, nitrate does not do this, because as soon as it's already a 1-. As soon as I stick a hydrogen on there, that's not an ion anymore. That's a compound, and that's nitric acid, which we'll talk about in our last unit of this particular series. But the other one that does this is, if I could erase, hold on, erase. The third one that tends to do this is phosphate. So you've got PO4, which is a 3- charge. Okay, so that's phosphate. So now if we have HPO4, that's going to have a 2- charge, and this is called hydrogen phosphate. Fantastic, that makes sense, or biphosphate if you really want to. There's another form of this one as well, and that can kind of throw you off. See how there's room actually for another hydrogen to join? You can do this, H2PO4, and it's still an ion. Oops, that's supposed to be a 1-. So this, H2PO4, it's the only one that does this. This is now called dihydrogen phosphate. And that makes sense if you think about what it is. Hydrogen phosphate has 1 hydrogen, dihydrogen phosphate has 2 hydrogens to it. And again, every time you add a hydrogen to it, you drop the charge down by 1. So those aren't too bad. They kind of make a lot of sense in terms of kind of what they are. But I wanted to point out that those do exist as another kind of way that's on there. Yes, it is possible. We are not going to cover it in here. If we have sulfite, which is SO3 2-, yes, you can also have hydrogen sulfite as well, or bisulfite. We're not going to cover that, but it is indeed a possible combination that you can do. So the only ones that we're doing the hydrogen versions of are the 8 form, are the ones that have that. Okay, so hydrogen oxyanions, or acidic salts. Okay, our next group. There's a couple of these that you just have to kind of look at. I just wanted to remind you of these ones. There's a few of these that are binary. And all of these have sort of annoying names to it. And the only reason I'm bringing this up, you have to kind of memorize these or be willing to use your resources on these. But it can be a little bit awkward because a lot of times the IDE ending means that the whole compound is binary. So like sodium chloride, sodium and chloride, usually the IDE ending means there's 2 and only 2 elements. However, there are a few of these polyatomic ions that were named IDE, I think before we realized that they actually violated those rules. And so these are hydroxide, cyanide, and peroxide. Peroxide's a total pain in the ass. I'm going to come back to this one in a second. Hydroxide and cyanide, these are just memorization ones. Hydroxide, hydrogen, and oxygen. Kind of makes sense. And it's a 1- form. But again, this is its own thing. It's not just hydrogen. Hydride by itself is a different ion than hydroxide. Cyanide is a little bit different. It's a deadly one. Carbon and nitrogen. That's cyanide. It kind of even sounds like a cyanide. I don't know, maybe that helps. But that's another binary polyatomic ion that's a little bit unusual. And then this one, thiocyanate, is just super annoying. Okay, it's annoying because it's got this ATE ending, but there's no oxygens present to it. It's super annoying. It turns out that thio usually refers to sulfur. One of the things that we'll see in another element, another polyatomic that comes up in a second. The prefix thio usually means that there's a sulfur. So this is like cyanide with a sulfur attached to it. SCN is thiocyanate. It should be thiocyanide, I know, but it's not. It's thiocyanate. So again, it's a little bit frustrating in terms of the name of that one. So it's cyanide with a sulfur on it, which is thio. And again, that may help you remember it. Probably not, but it may help you remember it. And then peroxide. Okay, we got to talk about peroxide for a second. So if you watched the video earlier on what mercury 1 is like, peroxide is very similar to this. So oxide is this, O2 minus. That's the normal oxygen ion, and that is 95% of the time the version that we will see. And then there's this one, oxygen gas. The elemental form of oxygen, the neutral form, is O2 with no charge, right? I'm not putting anything up here. That's just regular oxygen gas. Peroxide is like a combination of these two. Peroxide is super annoying because what peroxide is it's O2, 2 minus. Basically, it's this. Kind of like mercury 1 was a mercury 1 plus, but it was always a twin. Well, this is exactly what happens with peroxide. It's O with a 1 minus charge, but there's always two of them together. They always come in this particular form. It's a twin form called peroxide, and it's O2, 2 minus. So again, it's a little bit odd how that one is formed, and it's really annoying. So you can get some really unusual names or formulas, I guess. So if you want to think about sodium peroxide, you get sodium, which is a 1 plus, and then peroxide is a polyatomic. It's O2 with a 2 minus. So when you balance your charges out, you get Na2O2, and it looks really weird because this is one of those few times that you don't reduce down those particular names and formulas. Peroxide is definitely a weird one. Use a lot of caution with peroxide. Just so you guys know, when I give you a peroxide, if I were ever going to give you one, I would make it very clear that there was something that was going on, because it can be hard to tell with like type 2 compounds like this, CuO. Okay, in terms of figuring out what this is versus CuO2. We know that this is going to be a copper oxide. This is in fact copper 2 oxide. This one right here could actually be something funky. It could be a peroxide. It could be copper 1 oxide. There could be a couple of different ways that we could name this. So just be aware that when I give you peroxides, I will try to make it pretty clear. But peroxides are annoying. We'll do some practice ones of these in class. So peroxide, again, it's a twin where you've got two oxygens, each with a -1 charge, but they function as a polyatomic, as a pair with a 2 minus charge. Super weird. Okay, moving on a little bit. Here's a couple of additional other polyatomic ions that are out there. And again, these are ones that really don't follow any particular nice pattern. So they're a little bit annoying. And they have names that come out of different history in terms of where they come from. They don't follow our systematic nice naming rules. So acetate, if you guys had me before, you know acetate's Chiku, right? CH3COO minus is what it is. So I'm gonna draw it up here so you know what it is. If you came up from an inorganic background, C2H3O2 is the other way that it's written. I never write acetate like this, although you do see it like this from time to time. They're the same. It's written like this because it is one of these organic compounds, kind of like you can see in the background back here. It's CH3, like this, H, H, H. And then there's a C with an O up here and an O down here. It turns out this one's double bonded. And then this one is the one that actually does a bonding to something else. But this is why it's written as Chiku all the time. It actually kind of gives you an idea what the structural formula is of acetate. But we just call it Chiku. And that's one that you have to remember what it is. But like I said, I tend to write it that way because I have more organic chemistry in my background. And it's important in that particular aspect. So Chiku, otherwise known as acetate. Okay, chromate and dichromate. Chromate is this one, CrO4 2 minus. Dichromate's really unusual that this one exists. It's almost like a double chromate, almost. It's Cr2O7, not Cr2O8. It's Cr2O7, and it also has a 2 minus charge. So again, it's almost like a double chromate. So for me, that one's not too hard to remember. Oxalate's another one of these ones that's a serious pain in the butt. C2O4 2 minus. It is 2 carbons, 4 oxygens bonded together with an overall 2 minus charge. I don't know a plan for naming that one, whatever. Don't worry about it too much in terms of where that comes from, but C2O4 oxalate is the name of that one. And then thiosulfate. Thiosulfate's a dumb one because it's Again, got this thio on there and sulfur. Didn't I say earlier that thio meant sulfur? Yeah, it kind of does. So it's thiosulfate. So it's a sulfite with an extra oxygen to it. It's S2O3 with a 2- charge, and that's thiosulfate. It should be thiosulfite, but it's thiosulfate. I don't, whatever. Again, it's another one of those ones that's just super annoying to try to remember what they are. So these are a couple of our other polyatomic ions. There's no nice, neat pattern for these. Have your references out. Just be ready to recognize them, that when you see these ATE endings that you got to go look those up. Okay, last slide for today. Last one. So there are some additional polyatomics. There's plenty of oxyanions. There's plenty of polyatomics that are out there. If you Google like a list of polyatomic ions, there's I don't know, 50 of them or something like that. And the ones that we've talked about so far are these guys. And then we had chromium and manganese over here and chlorate. So I want to point this one out, that there are additional ones that are possible. And I talked about this particular pattern right here, that those ones had the 3 oxygens and everything else had 4 oxygens to it. So there are some additional ones. So this right here is chlorate. The one right below it, what do we got below there? Is bromine right there. Bromine, we did not learn this, but you can learn it really easy. So the way that this works is other polyatomic ions on the periodic table follow patterns of ones you've already learned. And in fact, they've followed the patterns closest to the one that you've already learned. So if we know what this one is chlorate, ClO3 with a 1- charge. Bromate is going to follow chlorate's pattern. Bromate is like that. Iodate, IO3 1-. And I can't remember what this one is behind there. Is acetate, I think, AT. ATO3 1-. ASTATATE. Acetate. Yeah, I know it's a horrible one to spell. But that's what that one would be. And tellurate, or no. Well, that would be tennessine. If it formed one, it would be TNO3- if it exists, but don't worry about that one. But these ones up here, these do exist. Bromate, iodite, and acetate do indeed exist. And again, they follow the pattern of the polyatomic ion closest to it. Similarly, this one and this one exist. I don't know the polonium one on there, but those other ones do exist. So this is Se, selenium, and this one is Te, tellurium. These do exist, and they follow the pattern of sulfate. So you could have SeO4, and it will have the same charge. Same thing, TeO4, 2-. Selenate and tellurate. And yes, they can indeed exist. So again, these two right here follow the pattern of the one closest to it. Similarly, right below here, we've got phosphate, PO4. Right below it is arsenic, ASO4, and it is, just like phosphate, a 3-. This is called arsenate. Again, it's going to follow the one closest to it. And then the last one would be this one right here. I just wrote over what it is. That's silica or silicate, the one that we've got. So Si, silicon right there, is going to follow the pattern of the one directly above it, which would be Si. Carbonate is CO3. So this would be SO3 with a 2- charge. So again, these ones in here are the ones that we know. Those are the ones that I would normally in an in-person class ask you to memorize those. Any of the other ones that are from the outside follow the patterns of the ones closest to them. So there you go. There's how you do the extended oxyanions, some of the ones from other parts of the periodic table, and any of the weird ones that would show up, over in this part of the periodic table are going to follow the same rules like chromium permanganate. So again, just a little bit of those extended ones. These are not on your polyatomic ions sheet. These do show up on the last 2 pages of the dry lab, and that's why I wanted to mention that these extended ones do appear out there. Okay, so there you go. One video left, and that's acids. So I'll see you in the last one. Have a good one. See you in a bit.